We're returning to the video after my phone call, and I think the last words I said on the last video is I can identify three parts or three locations. Location 1, where the blue mass is exited, but is still part of the control volume. Location 2, which is part of the control volume and still contains mass. And finally, location 3, which is part of the control volume, but the mass has left it. So the next part of our analysis is going to be to examine these three zones and write them in integral form. So let's examine now the extensive property, capital B. So in this case it's actually mass, but we'll use the letter B. And we want to use the definition of the derivative, which is the limit of a difference quotient, and that's going to provide us a guide. So for this control volume, we can write that for this system, the time rate of change of the property B of the system, if we're doing good old calculus, would be the limit as delta t vanishes of B at t plus delta t minus B at t divided by delta t. So that's the fundamental theorem of calculus. And from the sketch that we have, we can have the following. So B of t is equal to whatever the value of B in the control volume was at time t. Duh. But let's look at B at t plus delta t. So B at t plus delta t, the actual value of it hasn't changed, but it now is partitioned into different parts of our diagram. It is including the amount of B in zone 2 plus the amount of B in zone 3, and that's at time level t plus delta t. The total amount of B hasn't changed. We can write B2 plus B3 as, well, that's equal to the amount that's in the control volume right now minus whatever amount used to be in zone 1 plus the amount that's now emerged in zone 3, all at t plus delta t. So now in terms of the intensive properties, so this is an extensive description, but the intensive properties are dB dt equals the limit as time vanishes of the integral over the control volume of beta rho d volume evaluated at time level t plus delta t minus the integral over zone 1 of beta rho d volume evaluated at time level t plus delta t plus the integral over zone 3 of beta rho d volume evaluated at time level t plus delta t minus the integral over the control volume of beta rho d volume evaluated at time t, that whole thing divided by delta t. So that's, I'll just examine what that results in. The first term is the rate of change of beta in the control volume. and it's referred to, I refer to it as the volume integral, and then the remaining terms are going to be flux integrals. So let's go ahead and expand this. This is equal to the limit of delta t going to 0 of the integral beta rho d volume at t plus delta t minus the integral beta rho d volume at time level t over delta t plus the limit delta t goes to 0 integral over zone 3 beta rho d volume at time level t plus delta t over delta t plus the limit as delta t goes to 0 of the integral over zone, minus the limit of zone 1 of rho of beta rho d volume at t plus delta t over delta t. Okay, with all that in mind, we'll proceed forward. And this first term, this integral is the volume integral. So this part, which is circled now in green, this limit, that limit is the time rate of change of the integral over the entire control volume of beta rho dv. And I refer to this as the volume integral. And shortly, this designation, volume integral and flux integral, should make some sense in the context of what we have remaining. Okay, these other two parts, we're going to have to examine them more closely. Okay. So let's continue with redraw our sketch yet again. So here's my control volume, fixed in space. And I'm going to have my volume of blueness that's leaving it. Okay, so there's the blue part that left it. And now I'm going to introduce some area vectors. We'll call this one D area left, or D area 1, and DA2. So DA1 is the magnitude of that is whatever the area of that left face is, and the direction of it is pointing outward from the control volume, so in this diagram to the left. And DA2 its magnitude is the area of the right face of the control volume, also pointing outward from the control volume, hence to the right. So now we're going to apply Gauss's divergence theorem. You would have had that in physics and calculus 3 or 4, as well as I think in dynamics. So we're going to look at what's going on here in zone number 1. So in zone 1, Gauss's divergence theorem tells us that the negative of the integral over zone 1 of beta rho d volume at time level t plus delta t by Gauss's divergence theorem is equal to the negative of the integral over the control surface. So volume, we're about to switch to surface, of beta rho delta L times dA1. Now, what is delta L? Delta L is the distance that the blue rectangular or parallelepiped traversed in the time interest in the time interval delta t. So at time 0, the blue and the black were aligned. A short time delta t later, the blue has traversed in this picture rightward relative to the black, and the distance it traveled was delta L. This is essentially Gauss's divergence theorem. It's not essentially, it is Gauss's divergence theorem. Now for zone 3, we have the integral over zone 3 of beta rho d volume at time level t plus delta t is equal to the integral over the control surface of beta rho delta L dA2. This is also Gauss's divergence theorem. Why is 1 minus and 1 not minus? This one's taking on the negative signs because we're evacuating the area. So there used to be mass there and now there isn't. So it's a negative quantity. Whereas out here in zone 3, there used to be nothing there and now there is something, so it's a positive quantity. So in the limit, delta L over delta t is just the velocity. So the limit as delta t vanishes of the integral over zone 3 of beta rho d volume with respect to time by Gauss's divergence theorem is equal to the limit as delta t vanishes of the integral over the control surface of beta rho delta L over delta t dA2 delta L over delta t is simply the velocity at this face. In this case, we'll call it v2. We can play the same game with the negative part, and we have the limit as delta t vanishes of minus zone 1 beta rho d volume over delta t is equal to the limit as delta t vanishes over the control surface with a negative sign of beta rho delta L over delta t dA1, and in this case this is also, we'll call that the velocity at location 1. So now we're going to want to examine the relationship between these small areas and the velocity. So I'm just going to look at it from this direction. So what I see from that direction is simply a rectangular object. Left face I've labeled as 1, right face I've labeled as 2 to be consistent with how I set things up. And what I see in the left face is an outward pointing area vector, dA sub 1. Right face, an outward pointing area vector, dA sub 2. I see the velocity at 1 is this value. It's pointing inward to the object. The velocity of 2 is that vector. It's pointing outward from the object. And this boundary is the control surface. So what we have right here is minus, we have minus V1 times dA1 at section 1, and we have V2 times dA2 at section 2. And the minus sign is a consequence of the velocity vector pointing inward and the area vector pointing outward. So these are opposite in sense. Sense is in direction. So if they're opposite direction, a minus sign is associated with it. On the face labeled 2, we have the velocity direction and the area direction have the same sense. They're pointing the same direction. So that gets a positive value. Okay, so to put that in some sort of algebraic context, on the left face we have minus V1 dA1 happens to be equal to the vector V dot dA evaluated at location 1. On the right face we have V2 dA2. It too happens to be equal to the vector V dot dA, but evaluated at location 2. You notice the inner product, the sign convention is a result of the dot product, and this representation is how we will put it into the final equation that we want to use. Leave that there for a few seconds. All right. So now, believe it or not, we have all the pieces we need to represent the behavior of the entire system in terms of the integrals we've just defined. And so we want to collect all these terms in the original equation, and what we essentially have is what's called the Reynolds transport theorem. So dB dt of the system is equal to the volume integral, d by dt, integral over the control volume of beta rho d volume, plus the integral over the control surface. So this was zones 1 and 3 in our previous diagram of beta rho, and we've just demonstrated to ourselves that the zones 1 and 3 can be entirely collected into the term of V dot dA. So this is the fundamental formula for Reynolds transport theorem. So conservation of mass which is our first part, is capital B is equal to capital M, the total mass of the system. Beta, the intensive property, is mass per mass, so it happens to have the value of unity. And finally, we write the m dt of the system. Okay, so what do we know from our other mechanics classes? Mass is neither created nor destroyed, blah, 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 converted to other stuff, and before you know it, you have light-emitting diodes. The rate of change of mass in a system, by definition, is equal to 0. And that happens to equal d by dt, integral over the control volume of rho dV. Where'd the beta go? Well, its value is 1, so I didn't write it. Plus the integral over the control surface. Beta's 1 now, so rho, and then the result of the dot product V dot dA. And that is the Reynolds transport theorem applied for mass. Now, to get consistent with the words I'll use, this is the volume integral. And this is the flux integral. And usually there's multiple flux integrals, so I'll write it as a plural. It's the flux integrals. So look at what the calculus is saying. It says that the total mass in the system is equal to whatever the rate of change of mass is in the volume. So it either leaves volume, enters volume, plus the mass flux leaving or entering the volume. Well, if we keep track of what's in the volume plus what's entering plus what's leaving, mass can't change. The rate of change is 0, which is what we're after. So we'll now summarize that in words, which again is consistent with chapter 5 of our book. So in words, I'm going to go ahead and put a wiggly line here to indicate that. So we're going to apply a similar analysis for momentum, angular momentum, and energy. We probably won't go into the zones 1, 2, and 3 at that point because we've just demonstrated to ourselves that this expression up here is valid for any intensive property. So as long as we can describe the velocity field and we know what the intensive property is and we have a state equation for the density, we can apply that for any intensive property of interest. So conservation of mass. A pretty important concept. It works in civil engineering, environmental engineering, mechanical engineering, electrical engineering, and probably even financial engineering. Conservation of mass simply states that the rate of accumulation in a control volume is exactly balanced by the net inflow. So let me write the calculus version. d by dt, integral over the control volume, rho d volume, plus the integral over the control surface of rho v dot dA equals 0. So let's look first at the volume integral. This is simply the rate of accumulation of mass in the control volume. These are the flux integrals. This is the rate of net mass inflow. It's actually another way to represent it is NFLO. It's minus inflow as a rate plus outflow as a rate. And then everything is equal to 0. Another way to look at these in words is this is the rate of change of storage plus outflow rate minus inflow rate equals 0. Or the last way to memorize it, if this helps, is inflow rate minus outflow rate equals the rate of change in storage in the system, in the volume. So a couple of quick word examples. Imagine, if you will, a bathtub with a a nozzle that brings water into it, and a hole in the bottom that takes water out. So if the rate of water coming into the bathtub, the inflow rate, is bigger than the outflow rate, we're going to get a positive rate of change of storage. Water is going to store in the bathtub, and the water level is going to go up. If the opposite is true, if outflow is bigger than inflow, presumably there was water already in the bathtub, it will start to drain. And like I just said, it also applies to financial engineering. If the inflow rate is your monthly salary and the outflow rate are your monthly expenses, if your monthly expenses exceed your inflow rate, the amount of money you have in the bank is going to change negatively. And unlike real physics, the banking system lets us have negative money, and so that guarantees it will be working until the end of time. So you can think of the storage element as your savings account. If what comes in is bigger than what goes out on a monthly time level, say, then your savings account gets bigger and bigger. If what comes in is smaller than what goes out, then whatever savings you have gets smaller and smaller and smaller. So that concludes the introduction to the Reynolds transport theorem.